You're welcome to today's class. We're looking at electronic configuration in chemistry. Now, after this tutorial, you will find out that electronic configuration is easy. You need to acquire the right mental attitude, number one. Number two, you need to acquire the right mental information for you to be able to answer questions without stress in electronic configuration. Now, the mental attitude is a positive attitude. The I can do it, I shall do it attitude. And the right informational mental attitude is what we want to give you. Right informational mental information is what we want to give you now. Number one, I said acquire the right mental attitude. Number two, acquire the right mental information. That's what I mean to say. Now, in this concept, there are two major types of electronic configuration. Now, you have the structural configuration, and you have the orbital configuration. So, structural configuration and orbital configuration. Let's go to the first one, the structural configuration. Now, in the structural configuration, you notice that atoms of elements, they have what we call shells or orbit. And in those shells and orbit, electrons revolve around that shell and the orbit. An example of atom of element, plus negative, having shells, having electrons revolving around the shell. That's the structure of an atom. Now, we know that the atomic number determines the number of electrons that will revolve around the shell of a ground state atom of element. Notice the word I use, ground state, because an excited atom of element is different from a unexcited or a ground state neutral atom of element. Now, for instance, let's take sodium. Sodium is atomic number 11. So, the structural configuration should be the first shell contains 2 electrons. The second shell should contain 8 electrons. I'll tell you why. 2, 3, 4, and 8. So 8 plus 2 is 10. Now it remains 1 to be 11 because the atomic number is 11. So we're going to put 1 here. So this is the structural configuration of sodium. So this is 2 is to 8 is to 1. Now, what happens when the sodium becomes charged? When the sodium becomes electrically charged and ions, it will lose an electron. Losing an electron, the structural configuration will change. It will become an isoelectronic configuration with neon. What I mean by that, I'll show you. Now, sodium will now change from this configuration 1, 2, 3, 4, 5, 6, 7, this. Now, this is the new configuration. Why? Because the outermost shell electron has been lost. So the new configuration is 2 is to 8. Now, this configuration is isoelectronic. It's isoelectronic with neon because neon is an octet. Neon is a noble gas and it does not undergo any reaction because noble gas hardly react or they don't react. Now, it has an atomic number 10. Now you can see that the structural configuration of neon and that of sodium, positively charged sodium, is the same thing. Look at it now. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. You can see 8 electrons in the atomic shell, 8 electrons in the atomic shell, 2 inside the shell. Now, that is an explanation of structural configuration. Find the atomic number of that element and then look at the element. Is it an ion? Does it have a charge, positive charge or negative charge? Maybe chlorine. Let's use chlorine now. Chlorine is 17. 17th atomic number, the structural configuration of chlorine is this. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Now, 8 plus 2 is 10. It remains 7 for the atom shell to be completely filled. So I have 1, 2, 3, 4, 5, 6. Now, the atom shell of chlorine is now filled because the configuration is 2 is to 8 is to 7. 2 is to 8 is to 7. That's the configuration. Now, for this chlorine, this is the configuration for this one. But when the chlorine, let's give you a little example. But when the chlorine gives out electron, this is chlorine negative charge. When it gives out, when you receive an electron, if you receive an electron, it becomes negatively charged. Now, look at what will happen. What you do, 1, 2, the chlorine, let's solve the problem. When this chlorine, atomic number 17, receive an electron, it will become 18. 18 electron will be in the outermost shell. 8 electron will be in the outermost shell. But the total electron will be 18. So we have 2 here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, this is 2 plus 8, that's 10, plus 8, that's 18. This becomes an isoelectronic with argon. You see that? This becomes an isoelectronic with argon. So that's how it's been done. This is known as structural configuration. And then some questions may come to you. I saw a question in one of the exams, UTME exams in West Africa, Nigeria, which is 1994, number 12 question. 1994, number 12 question, UTME. If you are exposed to that question, or if you are disposed to it, you can check it out. 1994, number 12. They gave a structure. They gave this structure. This is the structure they gave. They say which of the elements listed, A, B, C, a lot. They said which of the elements listed has this structural configuration. Now, what is the atomic number for magnesium? 12. Now count the number of electrons. This is 2, 8, 8, this is 2, 10, 10 plus 2 is 12. So this is the answer. Very easy. Now let's go to the orbital configuration. You need to pay attention in that one. For the orbital configuration, are you with me? Are you there now? For the orbital configuration, you need to have some certain ideas. The first thing you need to know is about the energy levels. You need to know about the energy level, the S, P, D, F, energy levels. Now, these energy levels has certain amounts or number of degeneracy according to magnetic quantum number that the s orbital has 1/4 degenerate, because the magnetic quantum number helps us to know the number of degeneracy that is in the subatomic energy level. Now, the s orbital has 1/4 degenerate. The p orbital has 3/4 degenerate. The d orbital has 5/4 degenerate. The f orbital has 7/4 degenerate. Alright, now the s orbital can only contain 2 electrons according to Hund's rule. Hund's states that electrons fill in the orbital singly before pairing occur. So just 2 electrons, this one should be 6, this one should be 10, this one should be 14. But let's look at what we have. Let's look at the s orbital. This s orbital is the first shell the first energy level. So we have 1s. The p orbital is the second energy level. So we have 2s, and then we have 2p. The d orbital is the third energy level. So we have the 3s, we have the 3p, then we have the 3d. The f orbital, or the energy level, is the fourth one. So we have the 4s, 4p, 4d, and 4f. Now, this is where your configuration, some of the questions you'll be having, if it's a UTME exams, this is where the questions will stop. But if you want to go higher, we can have the 5s, 5p, 5d, and 5f. We can have 6s, 6p, 6d, and 6f. We can have 7s, 7p, 7d, and 7f. Now, you notice that the electron, according to Afabau's principle, it says electron filling the orbital from the lower energy level to the higher energy level. What's the lowest energy level, which is the s? Electron will start filling it from here. 1s. After the 1s, you have the 2s. I want to use another pen. After the 2s, you have the 2p and the 3s. After that, you have 3p and the 4s. After that, you have 4d, 4p, and the 4 and the 5s. After that, 4d, 5p, and 6s. After that, 4f, 5p, 6p, and 7f. After that, 5f, 6d, and 7p. After that, 6f, 7d. After that, 7f. Afabau's principle states that electron filling the shares from the orbital from the lowest energy level to the highest energy level. While one screw says electron filling the orbital singly before pairing occurs. Now, having that knowledge, we want to find what if you are asked what is the electronic configuration of sodium. Let's take sodium again. Sodium is atomic number 11. Now, we are going to write the this is the orbital configuration. Okay, you know I've discussed the structural configuration. This one we are discussing now is the orbital configuration. Hope you didn't forget that. The first one we did structural configuration. This is orbital configuration. Now the orbital configuration or the SPDF configuration. Now you are taught to represent sodium not in the structural configuration. You already know what the structural configuration is. In the orbital configuration, what you are going to do, you start off with this is it. You can start off like this, 1s, and if it is the 1s has 1-4 degenerates, which means it's just 2 electrons over there. So it's 1s2, and then the next thing is the 2s. 2s, s has 1-4 degenerates, so it's 2 electrons over there. It will be 2s2. And then I want to ask you a question. Is this 2 plus 2, that's 4, is it up to 11? The answer is no. We are going to the level 11 number because atomic number is 11. Now we have 1s2, 2s2. The next thing is 2p. So we have 2p. Now p has 3-4 degenerate, which means 6 electrons will be there. So it is 2p6. And then we have the next thing is 3s. So 3s2. Remember, it's not 2 now. 3s1 because 6 plus 4 is 10 plus 1 is 11. But if you want to represent it using these degenerate orbitals, you will now represent it like this. This becomes 1s2. This becomes 2s2. Okay, make a space for myself. This becomes 2p6. Or let's do it again. Let's do it again. This becomes 1s2. This becomes 2s2. This becomes 2p6. Remember 3-4 degenerate. This becomes 3s1. Now, you begin to fill in the orbital singly. Don't make a mistake of filling it in like that. Take it a poco, little by little. Fill in the orbital singly before you continue. Can we go now? Let's get it going. Let's get it going. So we have this, we have this, we have this, we have this, we have this. Notice singly first before pairing according to one stream. and then we have this. Of course, this is the orbital configuration of sodium neutral charged atom. Alright? Now, if you are giving a positively charged sodium, an ionized sodium, now the answer to that will become, let's do it, this will become 1s2, okay, 2s2, okay, 2p6. Should we put the 3s? No, because the 3s electron, that electron is lost. The electron becomes 10 instead of 11. So the 3s is off the record. So what we have, what we're going to have will become in the orbital configuration 1s2, 2s2, 2p6. So this is where we are going to stop. You fill in the orbital now. 1, 2, 1, 2, 1, 2, 3. 1, 2, 3. So this is the electron configuration of a charged sodium. Let's pick anything. Let's pick magnesium. What's the electron configuration of magnesium? Let's say the electron configuration of magnesium neutrally charged. Magnesium has atomic number 12. Okay? If it's atomic number 12, let's write everything together. The orbital configuration, let's put everything together. We have the first one is the 1s2. The second one is the 2s2. The third one is the 2p6 and it's 3-4 degenerate. The next one is the 3s. How many is related to the 10? 2. So if it's 3s2, we fill it in. 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, that's 6, then 1. This, that's 2. You see that now? Because this is 2. Open your eyes. Can you see? It's 2. Alright. So this is the configuration of magnesium. So you can write 1s2, 2s2, 2p6, and 3s2. Now, let's do another one. Let's do the electron configuration for chlorine. Let's do the one for chlorine. Now, chlorine has atomic number 17. Notice that this chlorine doesn't have a charge on it. So, the number of electrons remains 17. It's not going to change because the chlorine has no charge. So, let's do that now. This will become the 1s2. After that, 2s2. Why are we continuing? Because we are going to 17. Alright, that's what we are continuing. You get that now? When we get to 17, you pause. You stop. You stop it. Full stop when you get to 17. Now this is just for 1s2. Then next up 2s2. Next in line 2p6. Next in line 3s2. Is up to 17? No, this is just 12. Then the next in line is 3p. So this is 3p what? Will I put here? 3p5. Because 6 plus 4, 10, plus 2, 12, plus 5 is 17. Now, notice that the p orbital can contain 6 electrons because it has 3-fold degenerate. But I must not complete the 5. I mustn't complete the 5. If I get the number of electrons I'm looking for, I'll stop. Now, the number of electrons I'm looking for to complete 17 from this configuration is just 5. And when I get there, I stop there. Okay? Now, what I'm going to do in the orbital configuration, this is what we just have, is the 1s2, 2s2, 3p6, 3-fold degenerate, and then 3s2, and then let's put this one here. I need a space for myself. Okay, let's do it again. So this becomes 1s2, 2s2, 2p6, 3s2 for this, 2p5, 3-fold degenerate. Where's the p again? 3-fold degenerate. Now let's fill in the orbital. We have 1, 2, 1, 2, 1, 2, 3, 1, 2, oh, sorry, yeah. 1, 2, 3, 1, 2, 3. Singly before pairing. 1, 2, 1, 2, 3, 4, 5. Now, there is an unpaired electron. Look at this, please. There is an unpaired electron. And the number of unpaired electrons here is 1. Maybe you are asked to find what number of unpaired electrons, not the one that is whether the electron, I mean number of unpaired electron is in an electron configuration or is in an atom of element. So the number of unpaired electrons is just 1. So we want to go to do another one. Let's do more. Another one. Let's do chlorine negatively charged. Alright? Chlorine negatively charged, which means the atomic number, the number of electrons is now 18. 17 plus 1 is a negative, is receiving an electron, it becomes 18 by reduction. But the atomic number does not change. Atomic number remains 17. But the number of electrons can vary, it can change, depends on the reaction that is happening at that time. So we have this become 1s2, this become 2s2, this become 2p6. If you follow my order, this become 3s2, this become 3p6, this become, what's the next thing? It's up to 17. This is 10, 12, okay? 12 plus 6 is 18. So we're going to stop here. You see that? We're going to just stop here because we're looking at the electron to be 18. You can write the configuration to be 1s2, 2s2, 2p6, 3s2, and 3p6. Alright? Maybe you won't be able to see it. Let me make it very clear to all of you. Okay? 1s2, 2s2, over there, 2p6, over there, 3s2, over there, 3p6. Alright? So let's fill in the orbital. Here is 3-fold, don't forget that. Here is also 3-fold because the p orbital, according to magnetic quantum number, has 3-fold digit limits. So we have that 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3. Complete. Now, there is no unpaired electron in this thing. The number unpaired electron here is 0. It has 0 unpaired electron. I want you to try out this at home. Write a little configuration of this. Write from this. Then write from neon. Write for oxygen. Then you can drop the answer on the comment section. Also write for calcium. Calcium plus 2 charge. You can drop the answer on the comment section. But let's just do one more. At this time, we will take that one apoko. We'll take it little by little. Let's choose anyone. Let's come to calcium. Let's just do this for you. Let's do that. Calcium plus 2. Calcium has atomic number 20. But unfortunately, this calcium has a plus 2 charge. Alright? If we are going to do just calcium without seeing this atomic number, maybe we say we have calcium 20, no charge. Then the number of electrons that will be in those orbitals must be up to 20. But meanwhile, you have a plus 2. If there's a plus 2, the calcium is giving out 2 electrons by oxidation. Alright, so this calcium is giving out an electron. Let's do it for you. So calcium is giving out electron. 2 electrons at that by oxidation. Now what is going to happen now is that calcium will have, this calcium still have atomic number 20. Atomic number does not change no matter what's happening outside there in the electron. Now what is going to happen now? The electron will change. This will become 1s2, 2s2. Actually 2 minus 20 is what? 20 minus 2 is 18. So 18 is the one that will remain. So we have following that, 1s2, 2s2, the next thing 2p6, the next thing 3s2 is up to 18. This is 10. This is 12. Then what's the next thing, right? After the 3s2 is the 3p. 3p what? This is 10. 10 plus 2, 12. Average remaining to be 18. I think it's 5, 15, I think it's 6. Okay? Now, that's complete. Yes, complete. 1s2, 2s2, 2p6, 3s2, 3p6. That's complete. Now, you notice if you count this is 10. 10 plus 6, 16. 16, 17, 18. That's complete. So, the configuration now will be 1s2, 2s2, 2p6, 3s2, and then 2p6. Alright? So, but notice that this p is 3-fold degenerate. This p is 3-fold degenerate. So, we have 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3. So, having a pair electron is here, none, but this configuration is for calcium positively charged. Alright, don't be afraid. Look at the element. Is it positively charged? You remove the number of electrodes that is in that position number. Is it negatively charged? You add the number of electrodes that is there. In fact, find the one for sulfur minus 2. Alright, that means you are adding 2 electrons to 16, atomic number 16. So find it, drop the answer, any of what you can find, drop the answer in the comment section, we'll be waiting for you. This is all we've got for you in this video. Thanks.